Welcome to the Routing Basics module. In the last section, we segmented a large LAN or network into smaller collision domains using bridges and switches. Both of these Ethernet devices operate at the data link layer and use Layer 2 or MAC addresses to help manage and control traffic. Now we'll take a closer look, one layer up in the stack, at Layer 3, the network layer. We'll examine the differences between Layer 2 and Layer 3 and introduce you to routers, the network devices that operate at Layer 3. Note that either of the two symbols shown on screen can be used to represent a router. The symbol on the left is used to represent a small router. The symbol on the right is more frequently used to represent a router in network diagrams. We'll use this symbol to represent the router in the rest of the course. As in the previous sections, we will use Ethernet-based LANs and TCP/IP-based protocols in our examples. But you should keep in mind that other technologies and protocols do exist. You'll remember from the last section that each network interface card, or NIC, has a Layer 2 or MAC address assigned by the manufacturer. Devices might have multiple NICs or network interfaces if they require connections to more than one network. But every MAC address must be unique since these numbers are either assigned sequentially or generated randomly. There is no logical way to group them. Remember also from Section 2 that the first 3 bytes of the MAC address comprise the Organizationally Unique Identifier, or OUI, that every Ethernet equipment manufacturer is assigned by the IEEE. Here you can see that the network devices have NICs from different manufacturers since the OUI is different in each MAC address. In the previous section, you became very familiar with the actual format of broadcast and multicast MAC address. Now that you are familiar with what MAC addresses look like, we are going to make our diagrams a little easier to read. Going forward, we'll use just the last byte of each MAC address to represent the full address. As in the previous section, we'll continue to use the letters DA to label the destination MAC address and SA to label the source MAC address. If two devices on the same segment want to communicate, they must use MAC addresses. In addition to a Layer 2 address burnt into it by the manufacturer, each NIC or network interface also has a Layer 3 address assigned to it by the network administrator. Remember from Section 1 that the Layer 3 address that is analogous to the street name and a house number that the post office uses to deliver mail. Just like a residence, a Layer 3 address also has two portions, a network number and a device or host number. The network number is analogous to the street name, and the host number is analogous to the house number. Network administrators assign Layer 3 addresses, specifically the network number, to all devices in a network to introduce order. Layer 3 addresses provide a way of grouping network devices. For instance, Layer 3 addresses could be assigned to group network devices by building, by floor, or by functional group. On screen, you can see we have assigned Network 1 to this group of PCs. Notice that all the PCs connected to the switch use the same network number. We have also assigned unique host numbers to each PC. Note that in this section, we'll represent Layer 3 addresses with the networknumber.hostnumber format shown on screen. But as with the MAC addresses shown here, this is a simplified format. Here is one real-world example of a Layer 3 address and a Layer 2 address, contrasted with a shortened format we'll use in this section. As this section continues, we'll see how Layer 2 and Layer 3 addresses are used to route data within a network and across networks. In the previous section, we defined the term collision domain as a group of devices competing for network access. Bridged networks had collision domains with many devices. With the introduction of Ethernet switches, a collision domain might contain only two devices, an end-user device and an Ethernet switch. A collision domain is a Layer 2 domain because bridges and switches isolate traffic into separate domains based on the Layer 2 addresses in each frame. Moving to Layer 3, we find a similar concept. Layer 3 domains are called broadcast domains. A broadcast domain is the group of devices that can be reached by sending a frame addressed to the broadcast MAC address. You might remember we discussed broadcast MAC addresses in Section 2. The real broadcast address is shown on screen, but since we are using shortened MAC addresses in this section, we'll just use FF to represent the broadcast address right now. A broadcast MAC address is the address a device uses to send data to every device within a LAN, either directly or by way of a bridge or switch. When a bridge or switch receives a broadcast frame, it must forward it out every one of its ports. Each device in a broadcast domain has the same network portion of their Layer 3 address, and each has a unique host number. In the network shown on screen, the broadcast domain consists of all PCs connected to the Ethernet switch. If PC 1.2 sends a Layer 2 broadcast, the switch forwards this frame to all other PCs. Now let's take a closer look at how devices communicate using both Layer 3 and Layer 2 addresses. If PC 1.2 wants to send data to PC 1.8, it first determines whether the destination PC resides on the same Layer 3 network or broadcast domain. The PC looks at the network portion of the destination Layer 3 address and compares it with its own network number. If the Layer 3 network numbers are the same, the two PCs are in the same broadcast domain and can communicate directly. If the two PCs aren't on the same network, they can't communicate directly and will need the help of a router, which is a Layer 3 network device we'll get to shortly. Next, even though PC 1.2 already knows 1.8's Layer 3 address, it must determine 1.8's MAC or Layer 2 address. It does this by sending a Layer 2 broadcast frame to every device in the broadcast domain requesting 1.8's MAC address. This request has a special format which includes the sender's MAC address, the sender's Layer 3 address, the target Layer 3 address, and 00 for the target MAC address, indicating that the target MAC address is unknown. This broadcast is like yelling so that everyone can hear you. PC 1.8, are you out there? If so, what is your MAC address? All devices in the broadcast domain receive the broadcast frame and look to see if the request contains their Layer 3 address. Only the PC with the specific Layer 3 address in the request will respond. All the other PCs will ignore the request. In this case, PC 1.8 inspects the request and sees that it is the intended recipient. PC 1.8 creates a reply to let PC 1.2 know its MAC address. In the reply, PC 1.8 is now the sender, so it includes its MAC address as the sender's Layer 2 address and its Layer 3 address as the sender's Layer 3 address. Notice that the sender's Layer 2 and Layer 3 addresses always correspond to the device generating the request or reply. The sender's Layer 2 address will always match the Ethernet frame's source Layer 2 address as well. PC 1.8 then sends the reply back to the PC that requested it. Now the two PCs can communicate using unicast Layer 2 frames. These unicast frames are like two people whispering to each other so as not to disturb others. Now, you might be asking yourself, if the sending device already knows the destination device's Layer 3 address, why does it also need the Layer 2 address? Why not just communicate using Layer 3 addresses? The answer to that can be found in the concept of layering. Remember in Section 1, we introduced the network stack? In that section, we discussed how data moves down the stack of the sending computer and then up the stack of the destination computer. Each layer on the sending computer communicates with the corresponding layer on the receiving computer. When the data arrives, the receiving computer verifies that the data reached the correct destination before removing the header and moving up to the next layer. The data must go through each layer and it cannot skip layers. If we look at the model again, you can see that even though the sending device might know the destination device's Layer 3 address, the two devices must first communicate using Layer 2 addresses, since it is the last header and address information the sending computer adds, and the first header and address the receiving computer encounters when the data flows back up the stack. In networking, the process of using Layer 3 addresses to determine Layer 2 addresses is known as address resolution. In TCP IP-based networks, the protocol that manages that is called, fittingly enough, the Address Resolution Protocol, or ARP. ARP maps an IP address, which is a Layer 3 address, to a Layer 2 address. Other non-TCP IP protocols use other protocols to resolve addresses. On screen, you can quickly see that very large broadcast domains might cause network performance problems due to the increase in the sheer volume of Layer 2 broadcast data flowing between devices. To solve this problem, in much the same way network designers broke up collision domains into smaller segments, they break up broadcast domains into smaller, separate networks. But just like it wasn't possible to break up collision domains into smaller segments before switches were developed, breaking up broadcast domains also required a new network device, called a router. Where switches allow communication within a broadcast domain, routers allow communication between broadcast domains. Each broadcast domain then becomes a single, separate network. Within a group of interconnected networks, each network or broadcast domain must have a unique network number, just like the street name must be unique within a city. Each host on a network must have a unique host number, which is similar to a house number. Just as the same house number might be found on different streets, the same host number can be used on different network numbers. Here you can see that we have segmented our large network into 3 smaller broadcast domains or networks. Within each network, each device has a layer 3 address, consisting of its network number and unique host number within that network, and each device has a layer 2 or MAC address. In addition, notice that each port or interface on the router also requires a layer 3 address and an associated layer 2 address. A router is a layer 3 device and forwards data from one network to another. To facilitate communication, routers must know how to reach other networks. Routers can learn this information dynamically using routing protocols such as the Routing Information Protocol, known by its acronym RIP, or the Open Shortest Path First Protocol, or OSPF, the discussion of which is outside the scope of this course. You can also statically configure this information on the router. With either approach, a router stores this network location information in a routing table that includes all possible destination network numbers and how to reach them. Each entry in the routing table includes the destination network number, the next hop along the way to the destination network, and which port or interface on the router should be used to reach the next hop. The next hop address either indicates that the destination network is directly connected to the router or provides the address of another router on a directly connected network. When a router receives a packet, the router uses the routing table to make intelligent decisions on where to send the packet next. In this example, the router connecting Network 1 and Network 2 receives a frame on port 1. First, it examines the destination MAC address to see if it is the intended recipient. Because the frame is addressed to the router, it strips off the Layer 2 frame to inspect the Layer 3 addressing. The destination address is 3.2, so the router consults the routing table to find out where to send data for Network 3. It determines that it needs to send the packet to the next hop router, which is addressed 2.2 out port 2. At this point, the router adds a new Layer 2 frame, including the source MAC address and the next hop router's MAC address. We will go into this process in greater detail in the next section. Notice that this router only knows the next step or next hop to the destination network. It does not know the complete path. Through individual routing decisions made by routers at each step along the way, the data eventually reaches its destination. What if the router receives a packet destined for a network not in its routing table? Here, we see that the router has received another frame on port 1. Since the frame is addressed to the router, it strips off the Layer 2 frame. In this case, the destination address is in Network 5, but there is no entry for Network 5 in the routing table. If the router does not have a route for a destination network number, it will drop the packet and might send an error message to the sending PC. To avoid this situation, many network administrators configure routers with a default route that tells each router which way to route a packet if it encounters one with a network number it doesn't have listed in its routing table. In this example, we've added a default route to the routing table that specifies that data addressed to any unknown network should be sent to the next hop 2.2 out port 2. The router adds a new Layer 2 frame so it can send the data to the specified next hop router. Perhaps the next hop router will have a route to Network 5 in its routing table.